Hi, my name is Dr. Craig Swanson, and I'm a practicing wave doctor. This training video is the first video you should watch in the Getting Started with Wave video series. It's very important, however, that you familiarize yourself first with the Wave screen interface walkthrough before viewing the video. If you've not taken that step, I highly recommend that you take a few minutes right now to do that. The ideas that I present in this video will build on the information that's been presented there. Here's what I'll cover in the next 30 minutes. After a brief introduction, I'll share how I evaluate corneal topography maps and how they impact the lens design. I'll review opening the Wave software and how to properly enter the refractive data, and then briefly go over the differences between the axial and tangential tear layer mode. Once these pre-design issues are covered, I'll show you how to actually design a single vision lens and the subtle adjustments that can be made to finalize the design. I'll also discuss how to add a multifocal component into that design. Finally, I'll go over the steps I take to review the completed design before actually ordering the lens. So let's get started. Welcome to this video introduction to designing a basic wave contact lens. Now that you've had the opportunity to learn about some of the fundamentals of wave design and you've seen many of the unique features that wave software has to offer, it's time to look at how to put some of those concepts together and actually design a lens. In this video, I'll break down the basic fitting approach into different sections to help walk you through the basic process of designing and ordering a wave lens. Generally speaking, there's no one absolute design that is perfect for every patient, so this video is really meant to provide you with a basic foundation for designing. What's great about Wave is that you now have the power and the capability to create unique lens designs that you never thought were possible when you first learned about contact lens fitting. I would encourage you to regularly visit the Wave video resources page and become an active participant on the Wave Google group. You'll find a wealth of knowledge and invaluable insights there. Most of the questions or the problems that you may encounter can be addressed through those resources. Now it's time to have some fun and actually design a lens. Before you start designing, it's important to look closely at your topography. Remember that a wave lens can only be as good as the data that it's designed from, so getting a really great design quality topography is very, very important. Clinically speaking, poor topographies can cause all kinds of problems. They can result in fitting and lens positioning problems, lens rotational issues, comfort issues, and unpredictable over-refractions. So starting with a great topography and an accurate refraction will give you the best chance of a very successful lens design. So back when you're doing your exam, when you're first capturing those topographies, I highly recommend that you get 4 or 5 good images to compare. And if you're refitting a current RGP patient, I'd recommend that you have that patient stay out of their lenses for 3 to 5 days or maybe even longer to allow that cornea to sort of relax and get back to more natural shape. This will help prevent a lot of future headaches for you. So when looking at your topography, think about how to use the software to create a lens that will mirror or match the corneal surface. If we think back for a moment of how we were taught to fit traditional gas permeable lenses, we were told to fit a spherical, single curved lens to flatten out and compress that corneal surface. And if there was astigmatism, then we'd try to use 2 curves on the back of that lens to try to refit that eye. We'll think more in different dimensions with Wave software. First of all, you want to think about the shape of the cornea. So if we look at our topography, first of all, you want to think about whether the cornea is symmetric or not, or if it's irregular. So this is a pretty symmetrical cornea. Do you have irregular areas? Do you have areas of severe elevation or big flattened areas? Is the image centered or decentered? This one is rather well centered. Is there astigmatism, and if so, is it more centrally located or is it more limbus to limbus? You also want to think about which meridian is the steepest and which is the flattest. This will help you to envision how that lens may drift on the eye once it's in the eye. Look at the quality of the topography. Are you missing data? Is it really a good design quality image? Remember, once again, most fitting problems can be minimized by having a great topography. And when you visualize how the lens will sit on the eye, it'll help you anticipate how the lens may or may not perform as predicted by the software. This really helps you troubleshoot later on if you need to make some adjustments. Now, if you're missing data or have some artifacts, for example, in this topography, you'll see we lose a little data way out here in the far periphery. Especially inferiorly, we have a little missed data, probably from lacrimal pooling during the image capture. You can actually fix and adjust some of these by using dots editing or some of the other processing features. The way to do that is to right click on the image and choose Photo Process, and that'll bring up the corneal rings or the mires a little individually. So what you really want to look for here is, are you missing mires? Are they distorted? Are they nice and even? Are they symmetric? And you can use some of these features down here in the lower left, like the eraser or the dots editing tool. Now some docs and wave designers like to use this on a regular basis, and other docs prefer not to use dot editing, and I think you'll find what works best for you. I like to at least look at the images, so if I click on dots editing, you'll see that it highlights the single ring, and if you go each ring at a time, following it out, you look for missing data. So in this one we have some really nice data across the cornea. You'll see when we get out here we've got a couple little glitches in the surface. Again, some docs don't like to micromanage these little irregularities. I like to kind of fix them as I go, so I go all the way out each mire and just kind of click on them and make a little adjustment for them. This is a nice ring here, and you start losing a little more data as we start getting out closer to the periphery. Once again, you can just drag them through and correct those. I'll fix a couple more here. And now when we start getting further out, now we start losing a little bit more of the data. And in fact, if we get out here, we really don't have any data. So if you get further out in those areas where they think the data is a little more questionable, you can actually erase it, or a lot of docs just like to delete it all and then extrapolate back out. So in this case, I'm going to try choosing to delete the external rings. Those last couple of rings, we'll just delete that data. And then we'll hit OK. And the rings look okay, we'll hit yes. We'll resave that one. And once that's saved, we'll re-click the photo process. Once again, it'll bring it back up. And now you want to extrapolate the data back in out to the edge of the cornea. So we hit extrapolate. Since this is the right eye, we're going to drop a couple reference points here right at the edge of the limbus. And now you've got nice even mires all the way out. So next, when evaluating the topography, you want to start thinking about whether or not you're going to try to fit this eye with a spherical or a RSIM or rotationally symmetric lens, a traditional two-curved lens, or a geometrically symmetrical lens or GSIM lens, or would a free-form back surface design be a better way to approach this cornea? And as you become more comfortable with the software, you'll see that you can be very creative in adjusting the lens parameters to help you fit even the most unique corneas. Lastly, before we actually open up the design software, you'll want to measure and write down the corneal diameter and save this for later. To do this, you simply right-click on the image again, choose Caliper. Next, place a reference point at the outer edge of the limbus, and one at the other end right across the horizontal. So jot that number down. We're going to use that a little bit later on. So now you're ready to open the Wave software and begin your designs. To open the software, simply click on the Wave icon in the upper toolbar to launch the program, and then the Wave logo in the center of the screen. As the software opens, it will provide you with the option of either averaging or not averaging the astigmatism. In most cases, Wave doctors tend to prefer using averaging. What this does, as Wave is importing the topography, it averages out the data along each meridian to make it a little more consistent. And in most cases, it works quite well. As you become more familiar with the software, there are certain times when you may prefer not to average the astigmatism. For example, if you have a good design quality topography and a complicated cornea or a complicated prescription, and you're hoping that that corneal surface will help the lens align more consistently, in these cases you may prefer to not average the astigmatism. For this example, we're going to choose average the astigmatism. Next, you'll have a dialog box that pops up with the refractive data. If you entered the refraction already in the database, it'll auto-populate the screen. If not, you can enter the refraction here in either minus cylinder or plus cylinder form. You can also enter the add value in this box if you are creating a multifocal lens, and click Continue. Now, I highly recommend when you're working on these patients that you use a diagnostic RGP lens as part of your diagnostic workup and get a meticulous over refraction with that. And you can use this data to help make sure that your refraction is spot on. And using that data, what you can do, there's a little tool down here in the tool options. If you click on that button, you'll see trial lens data. Select that one. And in this box, you can enter that trial diagnostic data. For example, if you had a patient who the diagnostic lens that you're using was a 780 and the lens was a -3 power and you had an over refraction of -1, you can enter that here. Where that is particularly helpful is if you have a very complicated refraction or no refractive data at all, or you just don't trust that refractive data due to a corneal distortion or an irregular situation like keratoconus. Sometimes you may opt to not even include the initial refraction and just use your diagnostic data to help out. But in any case, it really is helpful in making sure that you have the correct power on that contact lens. The next step is to look at the actual topography that was imported. If you look at the lower right-hand corner of the quad view and double-click on that image, you want to compare that image to the topography that you actually started with. Now in this case, if you recall, we averaged the astigmatism, so there's a little variation from this original one, topography, but it looks very close. If you would have chosen to not average the astigmatism, these two images would look virtually identical. So now you have the Wave software open, the refractive data included, as well as the topography data. Now that you have the software open, with the refractive information loaded, next you'll have to choose whether you want to view your designs using a tangential tier layer mode perspective or an axial tier layer mode perspective. To do that, right-click on the center, and it gives you the two options. The main difference is how Wave views the data that was imported in the software. Generally speaking, when you design lenses using the axial tier layer mode, the designs will be slightly steeper, with steeper curves and higher sag values. If you design using the tangential tier layer mode, your designs will tend to be a little flatter, with flatter curves and lower sag values. Both design modes can work very well. Clinically speaking, if you were to design a lens using the tangential tier layer mode, and then design the exact same lens using the axial tier layer mode, the tangential tier layer designed lens will tend to have fitting characteristics that are about a half diopter flatter in general than the axial design. My recommendation for you would be, until you get more familiar with the software and changes that you make in the software, I would recommend choosing one mode compared to the other one and stay with that mode until you're more comfortable. For this particular lens, we're going to choose axial tier layer mode. Now that we have many of the basic settings in place, we can concentrate more on some of the specific adjustments you can make when designing a lens. If you recall, earlier in our video, we measured the corneal diameter for this patient as being 11.3 millimeters. For most new Wave lens designs, I would recommend starting with a diameter that is 0.5 to 1 millimeter smaller than the measured corneal diameter. In this case, it would be somewhere between 10.3 and 10.8 millimeters. So for our case, we're going to choose from the drop-down 10.5 millimeters. Next, let's review a few of the features that are available in the software. If you recall, this green line represents the corneal line. The line above that is the 20 micron line. And this curved line represents the back surface of the contact lens. Generally speaking, you want to keep that curved contact lens line somewhere between the 20 micron line and the corneal line. In a perfect world, we'd like to see that contact lens line perfectly match or be parallel with the green line with a little bit of an upsweep, a little upsweep here toward the end for a nice tear pump. When you're looking at making changes in the software, be sure to concentrate on this upper right-hand corner of the software view. If we're looking at making changes in this 3 o'clock radius, which corresponds to the nasal side of the lens, you'll see that the nasal data is populated here in the upper right-hand part of the software, and the temporal data is viewed on the left-hand side. And that's noted by the N and the T. If you switch over to the opposite side, you'll notice now that the radius that you're looking at, which is the temporal side of the data, is actually now in the upper right-hand side of the software. And that's denoted by the T. And now the nasal data has moved over to the opposite side. So the point of that is be aware of which part of the lens you're working on and where you are looking to make those changes to be sure that you don't inadvertently adjust the wrong part of the lens. Well, next let's talk about the control points. You might recall that the red dot corresponds to the back optic zone of the lens. The blue control point corresponds to the intermediate curve of the lens. The pink corresponds to the bevel position, and the black corresponds to the bevel lift. If we look at the positioning of the red dot for the OZ, generally it's best to place that somewhere in the transition between the green and the blue area. On average, for most patients, this will fall somewhere between 6 and 6.5 millimeters. For our patients, if we drop a cursor here, you'll see that we are at about 6.5 or so on that temporal or the nasal side. Superiorly, we're somewhere around 6.5 or so. Temporally, we're a little further out, probably closer to 7.5 to 8. And inferiorly, if we look at that transition zone, once again, we're around that 6.5 mark. So for this patient, we're going to choose a initial OZ setting of about 6.5. And we're going to place the intermediate curve of the IC at about 1 millimeter beyond that at about 7.5. Now these positions can change based on your topography. So sometimes, depending on the appearance of your topography, you may want to go a little closer with the OZ or a little further out. And as you get more comfortable with the software and designing wave lenses, you'll be able to make those adjustments for each individual case. Next, we need to decide which design mode we'd like to choose. So if we talk about RSIM, which is rotationally symmetric designs or a spherical lens, a GSIM, which is geometrically symmetric or a toric lens, or a freeform design, which has multiple curves across the back surface to match each radius on that lens. Well, if we think about this patient, if you recall, we have about 5.5 diopters of corneal astigmatism. So fitting with an RSIM design is probably not our best choice. However, for demonstration purposes, we're going to still take a look at that. So if you were to try to design this lens using RSIM, we would click on the RSIM box, choose Tools near the bottom of the software, click on Current Settings, and allow Wave to design the best possible spherical lens that could be fit for this topography. If we look at the results in the horizontal meridian, you'll see that we are between the corneal line and the 20 micron line. We have a little bit of a downturning area in this between the blue and the pink dot, which is our traditional landing zone area. We have a little upturning on the opposite side, so we would anticipate this lens to be binding a little bit maybe nasally and maybe lifting up a little bit more temporally. If we look at the vertical meridian, you'll notice that we're well above this 20 micron line. So based on this, we would expect this lens to be a little bit uncomfortable from lens awareness and probably not be real stable as far as positioning on the eye. Our next choice might be able to choose the GSIM or the geometrically symmetric design. We'll once again choose Tools and Current Settings, and we'll allow Wave to design a 2-curved back surface lens for this patient. So once again, if we look at the horizontal meridian, you can see we have this similar appearance to the RSIM design where we have a little bit of downturning in this nasal landing area and a little upturning in the temporal landing area. But now if we click on that vertical meridian, you'll see we're very much better aligned through this area. We're below the 20 micron line, and we do have a pretty nice looking landing area here. So based on that, we would think that this lens would probably be a reasonably good fit overall in this patient's eye. If you'd like to look at the back surface of the lens, if you double click on the lower left of the quad view, that, if you recall, is our front surface of the lens, or the back surface of our lens. Usually we like to see a nice even contour across the back surface. And you'll see we're not too bad. We have a little bit of kinking in the surface there. If you want to make a little adjustment in that, the way you would do that is you would click on the quadrant control option up here in the corner, and change that to 25%. Now keep in mind, since we are in geometrically symmetric design mode, if you make a change in this radius, it's going to carry over all the way across 180 degrees to the other side. So if we go back over here, we can click down a couple times on that red dot and click up a couple times on the blue dot to get a nice smooth curvature. And you'll see that we also were able to at the same time adjust this temporal side. If we now look at that back surface of the lens, we've eliminated those little elevated areas. And if we go back to our quad view, you'll see now that that back surface of the contact lens in the lower left-hand side very closely matches the topography view in the right-hand side. I would expect that this lens would be fitting fairly well overall. In a perfect world, though, if you recall, we'd like to see this corneal or the contact lens line perfectly mirror or be parallel with the green line and have a little bit of an upswing here at the edge. So let's take a look at the freeform design and see if that will provide us any other options. So once again, click on Tools, Current Settings, and allow Wave to design a freeform back surface lens for this topography. Once the lens is designed, we can again look at that horizontal meridian, and you'll see once again, actually this case we have a very nicely aligned lens, almost perfectly mirroring the green line. If we go up to the superior meridian, you'll also see that we're very nicely aligned, especially in these landing zones. And if we go around the entire lens, we have a very nicely aligned lens all the way around. If we want to take a look at the back surface contour, if we double click on the lower left view, again this is the back surface of the contact lens, you'll see we have a nice, pretty nice smooth curve in this nasal quadrant, but we have a little bit of a lump right here in the temporal. Now again, many wave doctors prefer not to micromanage these little areas, but if you'd like to, you certainly can. If you go now click on that temporal radius, you'll see that the temporal data is now moved over to the right-hand side of the topography or the software. To make a change in this area, I would place this at 25%, quadrant control, and we can click down a couple times on the red dot and maybe up a couple times on the blue dot to smooth that out. And once again, we've changed only that one radius. And if we go back to our quad view, now you'll see that that lower left view very closely mimics the lower right view. And if we look at that lens all the way around, we'll see we have a very nicely aligned lens that I would predict would be very successful for this patient. At this point, I would recommend that we save the design. Click OK. Would you like to save? Yes. Choose Accept. Make sure that your lens is checked so it is saved. Click on Save. Then reopen the design. And now you're ready to make any additional changes to the lens design. In this section, let's look at some additional adjustments to consider before ordering your lens. As you may recall, we discussed how a well-fit lens will have a nice lens profile line that mirrors or is parallel to the green line all the way across the cornea. The most important area in this lens profile line is this area out here near the periphery, known as the traditional landing zone. That really corresponds to the area between the blue and the pink dot. Now in this area, what you'd like to avoid is any areas where the lens has considerable downturning shape or too much of an upturn. If we have too much variance in this particular area, it tends to lead to lens stability and comfort issues. So let's look at our design for a moment. If we look over here in the nasal radius, you'll see we're nicely aligned through that whole area. But if we look over the temporal side, you'll see we have a little more edge clearance. If we go around the lens, to adjust that, we can just go right around the lens. We'll take a look at each quadrant first. If we look over here, we can see we have a little bit of a downturning, so I'm just going to click up. Before we do that, I'm going to switch over here to 25% quadrant control, so that way I'm only adjusting that one meridian or the one radius. And I'm just going to click up a little bit on that pink dot, and we'll go right around. And here we are in that temporal area that's a little bit more elevated. So I'm going to bring this one down just a couple of clicks. and maybe just a couple clicks on this blue line or the blue dot, and you'll see that we're now very nicely aligned. And if we go around the entire diameter of the lens, you'll see we have a very nicely aligned lens all the way around. So next we want to look for a moment at this bevel position, the bevel lift. A good starting point for this, if we click on the pink dot, is to set this at about right around 4. You can see we're at 2.8 right now. So I'm going to click on 100% quadrant control, and we're just going to raise that up a couple of clicks. Now again, you usually like to start in the flattest meridian, which is usually the horizontal one. And so we're here. This is probably 3.6, so we're probably fine right there. And next we're going to look at our bevel lift. Generally for this you want a value that's under 10. Somewhere between 7 and 10 is probably adequate. And again, we're going to choose that flattest meridian, which is usually the horizontal. And I'm just going to bring that down a little bit to get it somewhere closer to 7 to 8 is where I kind of like to start with these. And maybe a couple more clicks. And we should be pretty good right there. So now we have a lens that's very nicely aligned all the way around. I would anticipate that this lens would be very successful in the patient. An additional feature that can be very helpful when fitting lenses is a feature that Wave has included in the software, which is the ability to create a back surface aspheric optical zone. This feature, known as shape factor, can be found right here in the little box next to the S. By choosing this feature, you're asking Wave to create a back surface aspheric optical zone. So to do that, you simply click on it and choose a value. Now it doesn't really matter which you choose, because all you're doing is asking Wave to create some back aspheric curvature on the lens. So I usually choose maybe negative 0.05 or plus 0.05. Either is fine. And then you want to choose Tools, Current Settings, and let Wave redesign the lens. So now Wave is creating a back surface aspheric optical zone for this patient. And one of the things you'll notice once it's finished designing, if we look now at our lens profile, you'll see we have a very nicely aligned lens, 360 degrees. You'll notice that this lower left view of the quad view, or the back surface of the lens, very closely now matches the topography of the cornea. If you click on that back surface of the lens, you'll see that the lens is now a very nice smooth transition zone through the entire 360 degrees. Generally speaking, most Wave designers will start off by not using aspheric back surface optical zones, and then make the adjustment depending on what they feel clinically might be necessary. As you become more proficient with the software, you'll find which works best for you and which you're most comfortable with. So for this, we're just going to leave it here in the aspheric back surface, and I'm going to go take another look back here at my landing zone. In this case, I might want to just bring this down a click, and I'm just going to go readjust my bevel position. I'm going to bring that back up to right around 4 or so. And if we look at my bevel lift, we're a little bit high. I'm going to bring that back down under 10. Try to get that down somewhere around 7 to 8 would be ideal to start with. Maybe a couple more clicks. And they're right at 8. So I think this is going to be fit very nicely for the patient. Now the last parameter you'll need to adjust is to choose the center thickness of the lens and the edge thickness. Generally speaking, edge thickness right around 0.16 should be adequate to reduce the chance of cracking or chipping at the edges. A center thickness somewhere between 0.18 and 0.2 is usually adequate. Now keep in mind, Wave calculates the thinnest possible lens design based on the refraction that you entered and the shape of the cornea. However, you may have to adjust this based on your impressions, but usually somewhere around 0.8 to 0.2 should be adequate to reduce lens flexure. Now you've got a very well lit lens design with most parameters added, and you're just about ready to order this lens. In this segment, we'll discuss how to create a multifocal lens. Now that you've learned the basics of creating a well-designed lens, let's discuss some important characteristics of multifocal design. Wave software is truly unique as it allows you to create a multifocal lens with almost any size optical zone, and the option of having the center for distance vision or the center for near. Most RGP lenses only allow you the center distant option. Well, a few points to remember when designing a wave multifocal lens. First, and probably the most important thing to remember, is that you have to start with a lens that is performing well, providing good distance vision, and most importantly, centering well. In the previous section, we did spend a lot of time designing a lens, looking for a lens that fits the cornea well and should center well based on this design that we've created. Whenever you start with a lens that fits well and centers well, you can avoid many of the compounded problems or challenges that come along with multifocal fitting. Secondly, it's helpful to know which eye is the dominant eye and which eye is the non-dominant eye. You also want to think about what the patient has been wearing currently. Are they over minused or under minused? Are they wearing monovision or previous multifocal lenses? When you consider the power for the patient, it's also helpful to maximize the plus for both eyes. In most cases, it's even adding an extra plus 0.25 or plus 0.5 in the non-dominant eye can be helpful. Now, in selecting a bifocal size, there is no one perfect place to start. Many experienced wave designers have their own philosophy, and as you become more experienced with fitting multifocal lenses, you'll find what works best for you. I generally recommend starting out, if you're going to use a distance center design, with a optical zone that's about 1 millimeter larger in the dominant eye and about 0.5 millimeters larger than the pupil in the non-dominant eye. So let's take a look at our design. First of all, we're going to add the multifocal power into this lens by clicking on the spectacle plane box. For this case, we're going to choose an add of about 2 diopters. We'll leave it on center distance and hit continue. To add the multifocal position in, click on the front surface curvature, and you'll notice that this little green line represents the pupil position. Now if you click around, you'll notice that in each radial that pupil position seems to move, that either represents a slightly decentered pupil, or more commonly it represents a topography that's a little bit off-centered. In any case, what you're going to look for is the average pupil size for this patient as captured by the topography. So in this case, if you look back at your topographical data, down here in the lower right, you'll see that the patient's pupil diameter is 3.72 millimeters. So if we were to fit this lens as a distance lens on the patient with a distance center zone, I would choose a starting size of about 4.7 millimeters. So if we look at this front surface curvature view once again, if we click on the red dot, this is the distance pupil size. We're just going to set this at about 4.7 millimeters. And now we have a distance zone which is approximately 1 millimeter larger than the patient's pupil size. If this were the non-dominant eye, I would probably start with about a 4.2 optical zone. And we'll just move that back down to about a 4.2, and you're all set. If you chose to design this as a center near design instead, you would once again click on the refraction box, and this time choose center near, and continue. In this case, I would recommend starting with the dominant eye approximately 1 millimeter smaller than the pupil size. So in this case, we'll just bring it down to about 2.7. And now you can see that you have a little smaller than the pupil. And for the non-dominant eye, I would start with about a 0.5 millimeter smaller. So now you have a lens design that includes the multifocal value, and you set the distance zone or the near zone depending which design you choose. And then you would simply click Save for this patient. One last point. Remember to be realistic with the expectations that you set with your patients. As with any multifocal lens, most patients can achieve good functional and social vision, but expecting perfect vision, both distance and near, can often lead to frustration. Remember, with Wave, you have a unique opportunity to create the most customized multifocal solutions for your patients. And we hope that you find that this video to be a helpful starting point when designing Wave multifocal lenses. Before ordering your lens, let's review your design. The lens diameter has been properly set at 10.5 millimeters. Your refraction has been entered, and the appropriate diagnostic RGP data has also been included. The lens aligns well, 360 degrees, and you have a nice edge profile and appropriate edge clearance. You've set the center thickness and the edge thickness appropriately. And now it's time to order the lens. So simply click on the order button and click yes. Now on this screen you have a few options. In this upper left-hand corner you can enter the patient's data, whether you want to ship the lens to the patient, how you'd like to ship that lens. You can choose the material in this drop-down. For example, if you want to choose fluoroperm 60 and you'd like to change the color of the lens to say green, you can choose to fenestrate or plasma treat. In this lower left corner, you can choose to send a message to Wave. For example, but just remember, any message to Wave will delay the lens order as the Wave needs to answer your message. Over here under clinical notes, this area does not go to Wave. This is for your own reference. You may want to include a simple note to yourself, any changes that you made. For future reference. And then click a choose accept. And now you'll be ready to order your lens. I hope that you have found this introductory video on basic wave design a helpful tool. Remember, there is no one absolute design for every patient. However, as you become more familiar with the power and the flexibility of the software, you'll find that you can now provide very successful custom lens designs for just about any patient. I would highly recommend that you regularly visit the Wave Video Resources page. There you will find many in-depth training videos which will help answer the most challenging questions that you may run across when designing lenses. And don't forget to join the Wave Google group. There you can interact and exchange many great ideas with experienced wave designers. Well, thank you for joining me on this training video, and I wish you well with your wave designing.